Alright, let's make a start. Welcome everybody to what month is it? May's meeting of the Astronomical Society of Frankston, and I'm chairing tonight. My name is Peter Skilton, for those of you who don't know me, new visitors, and feel free to come and say hello later on in the meeting when we do break. David Girling unfortunately has had to step down from presidency due to health reasons, but hopefully he'll be better soon. And Treasurer is currently touring in Europe at the moment for the next few months, and certainly tonight Jane McConnell will be acting Treasurer, and she'll put up her hand in the air over there if you're wondering who she is. We have someone taking notes for Scorpius, and I would remind you, those members who have been around for a while, you should be wearing your name tags so that others can get to know you. And if you are new arrivals to the Society and have joined up, John Cleverdon will prepare a name tag for you for the next meeting, and John is just down that side showing who he is, just so we know who you are. Tonight, as usual, the raffle, which I believe is going around, is $1 for a ticket, and the prize is 2 prizes, I take it. Who arranged the raffle? Yep, Roger. So both of those, first, second, third prize? Yep. So we have Target Earth, which looks like asteroid impacts, and cosmic dispatches, which are probably along the same sort of lines, and a bottle of Shiraz. Now, congratulations to those members who've reached various milestones. At the 5-year mark, we have Debbie Brady and Phil Holt and Max Barrett. 3-year mark, Julian Beaumont, and new members just joined, Stephen Garcia, Paul and Jackie Taylor, Tony Wolfe, Constant Ramsdell and Graham Hunt. Any here tonight? Well, welcome to you all. And what we'll do is, at the tea break time, someone will come and say hello to you and show you where to go and introduce you to the Society. And can I actually ask that someone to be Bruce? Yeah. And Bruce will put up his hand so you know who he is. And every meeting I'll pick someone different to act as chaperone for the new arrivals. Now, I trust you've all picked up your What's On, which is out in B6 format on the look of it tonight, showing you what's coming up in the coming months. If you haven't, then during tea break it's in the little Perspex holder on the end of the table. Library, as a reminder, is open in the hour before the meeting and also during the tea break as well. And our librarian will kindly put his hand in the air, which is Andrew sitting at the back there. And members are able to borrow materials from the library, and those materials might be books, binoculars, and also telescopes. Right, since last meeting, John, do you want to give a rundown?
Firstly, thank you to Sally said earlier for What's On, says I had an accident with my computer on the weekend and had to ask for a short notice to print them out, as Murphy has been following me around with computers recently. With recent members' nights, on Saturday the 19th of April, a couple of members went up to the Rise to watch the Ganymede Shadow Transit, and I was stayed at home. And on Saturday the 26th of April, there were about half a dozen of us up at the Rise, enjoying quite a good night there, and I was getting some practice for the Messier night. A few members also spent Anzac Day night at the Rise. On Saturday the 10th of May, there was a lunar night at the Rise, and also several members went up there, and at some stage at 3 AM. I had a job interview next week, so I couldn't make it to that. One of those members attending the lunar night was Frank with his new tenant stuff. And there was also the transit of Mercury, and I did some observing of that from around the place. Okay.
That's all right.
Sorry, just talk a bit louder. Unfortunately, the air conditioning is accidentally turned on tonight,
I know.
as you may have noticed.
Yeah, you need to.
I couldn't make it to the public night because of the cold, so I don't have any report on what happened there. Coming up, we've got the Messier night on Saturday the 31st of this month. As I've mentioned in the latest Scorpius, this is a chance for those with a bit of a competition in mind to find their way through a list of 82 of the Messier objects, and I've supplied a list over there, or you can download it off the internet. And if you want to find all 82, you'll need to stay at the rise till about 5 or 6 a.m. And if you do find the most objects from that list, you'll receive a certificate at next month's meeting. And you won't necessarily need a big scope like Greg's or a computer controlled one like Bob's, as I can see the faintest objects on the list with my 6-inch chromium. And even if you don't have a larger scope, you can come along and see it as a night to expand the number of Messier objects you have seen. And finally, the telescope learning day. Dave Girling will still do the contact for that, and the topic for the June telescope learning day will be observing Mars, and of course if that's a clear night you'll be able to observe Mars, and the next few months will be an excellent time for observing that. And note that as on the Watson, David's contact number will now be his home number for that. And also note that, and it's also on the Watson, I've now taken out from David Girling as the contact for the members tonight, so I'll put my phone number. Thank you.
Also, since we last met, I believe Warren Park Primary School was visited. Did that go ahead? Yep. About 100 students there. 110. And since the last meeting, the VASTROP was also held up at the Ballarat Astronomical Society. That's the Victorian Astronomy Conference / convention of amateur astronomers mostly. And I'll say a little bit more about that after tea break. Basically, the Ballarat Society have a new building on their site up there, and very impressive, virtually a brand new house actually. Members' nights we've just gone through. Astronomy classes, Ian Sullivan here.
Yes.
Do you want to say anything about that?
Yes, last year we started a theory class back in about July last year. It was actually a year ago, almost a year ago, and we used the community house at Mount Eliza. Then I had to go for an operation, and anyway, the Mount Eliza community house, they had problems. We couldn't run a session in August. I approached them again, and of course I had an operation and couldn't do anything with them the rest of last year. Then this year, I may approach them again, and it's not possible to get the community house, but there is a hall next door, and there is a room in the hall. The only thing is a bit expensive, but it can be got. The other thing, Don Leggett mentioned that no, it's not a go. No, it's not an option. No. So we've still got, there is a possibility then of getting a room in the hall at Mount Eliza. Now we've still some money in the kick from last year to run another session for the people who did it last year, and then I'll throw it open to everybody else. But anybody who's interested in theory classes on the celestial sphere, on theoretical astronomy, not telescope learning, the other aspect of it, basic optics, run sessions. Saturday afternoon was the day of the week that seemed to suit the people last year. I don't know if that's still the case. So if there are other people, if you give me your name tonight, if you are interested in theory classes, either on a Saturday afternoon or a Sunday afternoon, a matter of getting 3 or 4 people together, that's all. I don't expect large numbers. But it'll have to be that sort of number to justify hiring a room. Until we get our own premises, which we will ultimately have down there at the Rise, we are in the hands of being able to get somewhere. If anybody knows a venue, a place that we can hire at a moderate rate, then that's the options. I'm willing to donate my time. It's just a question of getting a venue, and there should be sufficient people interested. The people who did last year, I'll speak to them. If I don't speak to them tonight, I'll talk to them on the telephone in the meantime. Perhaps next general meeting I'll be able to have something positive, something definite to tell people. Please see me tonight if you're all interested in any theory course. Let me know what you're interested in. Thank you.
Thanks, Ian. The other thing that's coming up is this Friday night at Swinburne University. We've been invited along to their 3D visualisation centre. Roger, do you want to say a couple of words on that? I think there are still some spots available.
Yes, we've still got, we've got about 17 people at the moment. There's a maximum of 35. So anyone else who's interested in going, see me tonight. Starts at 6:30, runs for about, I think they're going to run for about an hour and a half. It's at Swinburne up in Hawthorne. I've got some directions on how to get there and where to meet. So anyone who wants to go.
We need another 3.
Sorry?
We need another 3.
Oh, that's right. We need a minimum of 20. So there'll be some more people coming.
Thanks, Roger. All right, well, with that, we'll move on to the main item of the evening, if Tanya is ready. Tanya Hill has visited us once before with her husband Alex, and she's the resident astronomer at the Melbourne Planetarium. And she's been there a number of years now, and came down and gave us an excellent talk a couple of years ago, and has kindly offered to come back and speak again. And I thank David Girling actually for arranging that. And without further ado, I would welcome Dr. Tanya Hill to come and speak to us, and I'm sure you'll make her welcome.
Well, thank you very much for inviting me back here again. It's always lovely to come and talk to people that are already so interested in astronomy. Just a little bit for those people who didn't come to the talk last time, or if you did, I think it was a couple of years ago now, I can't remember. My actual interest in astronomy started when I was in high school. And that was the first time that I got to use a telescope, and it was of course when Heale's comet was around in 1986. And so that was kind of when I got the bug and got hooked into spending cold nights out in my friend's own horses. So she had this big paddock that we used to drag this telescope out to, and just sort of tour our way around the sky. And I actually thought that that was where sort of astronomy was going to sort of stay for me. It was going to become the biggest bit of a hobby that I did. And it was, but I was very fortunate when I was at uni. I actually come from Sydney, so I was at Sydney University, in that I managed to get a vacation job at the Anglo-Australian Observatory with a fantastic astronomer out there. And that's basically then where it took off. And now the reason I smiled when Peter introduced me as Dr. Tanya Hill is that's actually a very new addition to the doctor bit, being that it was only December last year that I actually finally graduated with a PhD. So I did get the job here in Melbourne while I was still trying to finish up, so it ended up being a little bit more of a hurdle to finish that than I thought it was going to be. So it's like fantastic that it has actually sort of get a little bit of a buzz about it all. But I'm here tonight to talk about black holes. Last time I was here I talked about my actual research that I was doing, which is looking at distant galaxies and trying to decipher whether their energy was coming from a black hole or whether it was coming from what we call a starburst, these incredible bursts of star formation. And so I thought tonight, sort of to round things out, we just sort of spend a little while chatting about these exotic and amazing objects that we know of as black holes. So hopefully I'll be able to, some of you may well already know quite a lot about this, but hopefully I'll kind of be able to give you little tidbits that maybe you haven't quite heard before. And I'm also very happy for anyone to ask questions or things as we go along. But one thing again before I start the lecture, because at the moment my memory isn't so great. So I do want to let you know that I also brought along some info sheets, because in July and August we're actually having a couple of lectures at the planetarium if anyone's interested on a Thursday evening. And particularly the lecture in August, we're actually lucky enough to have a visiting professor from University of Arizona, Professor Fulvio Amelia, and he actually has done a lot of research into the black hole at the centre of our galaxy. And so it's kind of a nice little tie-in there. And the other thing, it's great that you're organising the trip out to Swinburne, because actually on the other side of my little sheets, the planetarium and Swinburne have actually got together to trial a continuing education course in astronomy, because basically you guys may well already know the CAE has actually stopped doing astronomy as one of their courses. So we're offering in the month of August a 4-week course where one session is held at the planetarium and the other 3 sessions are held at Swinburne. So just a little bit of information for you to know what we're doing out and about. But now let's get on to the real fun stuff. Let's talk about these weird guys called black holes. And I mean, the great thing about black holes is that they deal with gravity. And what's fantastic about gravity is that it acts on all of us. It's of course acting on us right now. It's anything that's got mass or even light will be affected by gravity. And so it's one of these forces that is really important in our universe. You know, if you think about some other forces, like an electric field, for instance. But it's only if you've got a charged particle that they're going to get very excited about electric field. Anything else, you know, isn't really going to care less. Whereas everything with mass is going to be affected by gravity. And so it's a really sort of important concept then, these things called black holes. And in actual fact, they've kind of been around for a long, long time. It was actually back in the 1780s that a couple of guys, a French guy and an English guy, first came up with the idea of something along the lines of a black hole. But what they were actually thinking of wasn't what we now call a black hole, but they were just kind of doing their thought experiments about what we call escape velocity. And that's roughly the speed that we need to be able to leave a gravitational field. So here on Earth, if we want to leave Earth, if we want to go flying off in a rocket and go and visit the International Space Station or do something interesting out in space, what we need to do is sit on one of these amazing bombs, really, that then accelerates us until we reach 11 kilometres per second. Of course, once we do that, then we can actually leave Earth's gravitational field and we're free from that. Or at least we can, so we can escape the gravity. If we think about things, okay, well, you know, Earth's one of the planets in the solar system. What about Jupiter? Jupiter's a lot bigger. It has a lot more mass, and therefore it's got a lot more, a bigger gravitational field. And so, of course, we need to accelerate to an even greater speed to leave the gravitational force of Jupiter. And for Jupiter, it's about 60 kilometres per second that we need to be travelling. If we go to an even bigger body with even more mass, like the Sun, we want to leave the gravitational field of the Sun, you want to be travelling at about 600 kilometres per second. And basically, these guys were thinking about this and going, well, what happens if you had a star that was so massive that the escape velocity actually equaled the speed of light? What then would that mean? And of course what it would mean is that not even light could escape from this body, and so therefore the light rays would basically bend back in on itself, and it would be a region that we couldn't actually see because there was no light coming out of it. But what their concept of this object was more along the lines of something more like a black star. Because what they were thinking was that if you had an object pretty much like the Sun, but 500 times more massive, then that object would have this escape velocity equaling the speed of light. And so they would be quite these large bodies out there in the universe that wouldn't let light escape from them. And so they in every other respect, I think they pretty much thought that they would be like stars. Except that, yeah, they just had these enormous gravitational fields. Now, of course, so this was back in the 1780s that these kind of ideas were floated around. But nothing pretty much happened for quite a while until good old Einstein came around in the early 1900s. And of course, Einstein, completely changed a whole lot of things in physics and in other scientific fields. And the important things that he did for us when we think about black holes was firstly that he gave us a better idea of how gravity works across these huge distances. And what he told us was, in fact, that these masses, by their gravity, that the gravity actually bends space. And I'm sure most of you have probably seen these kind of diagrams before, where basically you imagine that space is kind of a bit like a trampoline. If you put a big bowling ball in the middle of your trampoline, then you're going to get a depression where all that mass is from the bowling ball. And of course, that's how we now picture our universe is. That everywhere we've got these massive objects, space actually bends around them, and that's our idea of gravity. Of course, one of the things that's really hard is that these pictures always show these things more in 2 dimensions. And of course, we've got to try and grasp what it actually is like in 3 dimensions. And I have not at all come up with I'm sure lots of people haven't come up with any way that we can actually try and get that concept and work it out in sort of more 3 dimensions. The thing that was really important too for black holes is that, and that I'm going to come back to in a little while, is that Einstein showed that objects actually have what we call a gravitational radius. And basically that's the radius of an object where if it's that size, then everywhere on the object, the gravity approaches infinity. And that was another really important concept. And as I said, I'll come back to later as we continue moving on. Now, of course, the thing about Einstein, well, even as I was just saying, with trying to grasp how this actually works in 3D, how that works in sort of real life in our universe, is that, so much of what he says is more against our common sense. We find it very hard to experience it. But luckily, from his theories that he's put together, there are a couple of experiments that we can do that do show that pretty much he's on the money. He knew what he was talking about. And just quickly, I'll kind of digress to 2 of those things. And the first one, of course, was the precession of Mercury. And basically, haven't heard of this before, it was that we were pretty good at, working out where the planet should be, except for some reason, little Mercury, the closest planet to the Sun, always seemed to be a little bit off from where where astronomers predicted the planet should be. And it was always off by about 43 arc seconds. And it was very hard to try and work out what that was. I think one of the theories was actually that maybe there was another planet in between Mercury and the Sun that we couldn't actually see, that was actually putting Mercury off by that 43 arc seconds. And for any of you Star Trek buffs, that planet was actually called Vulcan from the door. I think actually Star Trek, you guys probably might know more than me, Star Trek actually took the name from that, didn't they? Well, I'm guessing it was that way around. I suppose considering Star Trek was in the 60s. But basically what it really was about was that what was happening was Mercury's orbit, you can see here some beautiful elliptical orbits, and rather than Mercury just following one elliptical orbit, Mercury's whole entire orbit was actually what we call precessing. And so in fact the orbit was moving around as the planet itself moved around the Sun in its elliptical orbit. And this precession is exactly predicted by Einstein's theories. And so there was, all of a sudden that 43 arc seconds that they could never quite capture where Mercury is was completely solved.
Excuse me, Tanya.
Yeah.
What is that a consequence of, or don't we want to know the answer to that?
Yeah, but we probably don't want to go into it right now.
Nothing that you can sum up in 6 words or less.
No, it's just pretty much looking at the gravitational fields and yeah.
Gravity, like.
Yeah, it's, good old Einstein. We came up with these things. The other thing that he showed was that, which was what I was saying before, is that light is also affected by gravity. And that was one of the important things, because as I said earlier, what gravity does is gravity is the one thing that anybody with mass, any object that's got mass, is going to be affected by gravity. Whereas light doesn't have mass. So it's like, well, why is light then affected by gravity? And of course the reason is because, well, your space is actually curved. And so when light travels in a straight line, but it's actually travelling through this curved space, then you get this apparent bending of light. And the best way to see this is to actually well, what this image here is showing you is that in fact just the gravitational field of our sun can actually bend the light from distant stars. So here we are here on Earth, and there's a star sitting up here, but the light, and it's actually directly behind the sun. So theoretically we shouldn't actually be able to see that star, it's blocked by the sun. But what happens is that because the light gets bent in the gravitational field of the sun, it gets bent around, so we actually do see that star. But except when we're here on Earth, we imagine that the star is actually here, because we always, think of light travelling in straight lines. And so you get this apparent notion of a star, when really the star hasn't moved at all. It's almost like we can see around curves because of this bending of space. And Einstein predicted all of these things in 1915, and apparently there was an eclipse of the sun in 1918. And so this was an opportune time to do this kind of experiment, because of course you've got your sun sitting there in the sky, except that with the eclipse, the solar eclipse, you're blocking out the light from the sun. So what this means is the gravitational field's still there, but you don't have the glare of the sun to deal with. And so you can actually see, are the stars in the right position, or have they apparently moved because their light has been bent around the sun? Now, sort of most books say that in 1918 they did this fantastic experiment and proved that yes, there was the bending of light and the stars did move. But unfortunately, looking back now at the data, we have realised that in actual fact they didn't have, their observations weren't accurate enough to really show that they had proved any of Einstein's theories. But luckily, in more recent times, we have been able to show that this is exactly what happens. So Einstein was pretty much correct in all ways.
One question before you go on. Is this light bending of stars totally different to the proper motion that they have?
Mm-hmm. Yeah. So
why wasn't the Mercury thing noticed before Einstein kind of came along? Is Mercury's thing also essentially proper motion, or is it a light thing?
No, it's not a light thing. It's the motion of Mercury orbiting around the sun. But the thing was that it was thought that Mercury would just orbit basically in an elliptical orbit, whereas no one had really. I mean, it's one of these things that when you look back now at the solution, it looks quite easy. But of course, no one had actually thought that what was actually, as Mercury orbited the sun, its whole orbit was precessing around. And that's where Einstein's equations predicted exactly that was going to happen. And so that's why it was like, the penny dropped kind of thing. Because they did, the ancient astronomers, that was the problem. They knew that they were always getting Mercury's orbit wrong. They couldn't work out why that it wasn't where it was supposed to be. And it was simply this precession that Einstein showed. Proper motion of stars is actually just the physical movement of stars through the universe or through the galaxy. Whereas what's happening here is that in the time frame, the star hasn't actually moved at all. It's just that we see it's an apparent movement just because its light's been bent. Okay, so that was, some of the indications that, Einstein knew what he was talking about. And so this helps then to kind of take a bit of a leap and say, well, hopefully he knows what he's talking about with this as well. And this is the idea of gravitational radius that I was talking about. And basically what we have, I've got a series of objects here. The first one in the top left is of course our Earth. And then I've got a series of stars in different their evolution, different parts of their life cycle. And basically in all these objects, you always have two forces. You've got gravity always pushing inwards, and you've got something pushing outwards, balancing that force of gravity. Now for good old Earth, you've got, again, gravity pushing inwards, but Earth has got a whole lot of pressure, elasticity, everything from the rocks that makes it up, that basically gravity can't push anything any closer together. And so it's quite stable. And so you've got this balance going on with our planet Earth. Over here, this is of course our closest star, the Sun. And what we've got there, again, we've got gravity pushing inwards. But with the Sun, there's all these nuclear reactions going on in the core of the Sun. And that's where these nuclear fusion reactions are turning hydrogen into helium. And that's the process that's basically giving the Sun its energy, giving it its light, and it's creating a pressure in the Sun that balances the force of gravity. And our Sun will be quite happy like that for the next 5 billion years or so. But eventually, those nuclear fusion reactions are going to run out. And when that happens, gravity's going to take over and gravity will push in. And there's a whole series of steps that goes on, but eventually our Sun will end up like this guy down here. And of course this is a fantastic planetary nebula, and probably a lot of you guys have seen them through the telescope. And of course they've got nothing to do with planets, but when they were first looked at through a telescope they appear disk-like, the same way that a planet appears as a disk. And so that's why they were given the name planetary nebula. And basically what we're seeing is a big shell of gas that's been puffed off as the star died. And right in the centre, you've got the remains of the core of the star. It's what we call a white dwarf. And what's happened to our little white dwarf is that gravity has taken over so much that it's pushed everything together, and by this time the star's mostly made out of carbon and oxygen. So everything's been tightly compressed together. And in fact, it's so compressed in a white dwarf that you basically have the electrons as tightly packed as they can go. All the little electrons can't move any further. They're as squished together as possible. And so that's where we're up to with the white dwarf. This guy over here is an example of what happens when a really massive star dies. And massive stars, as you probably know, die in supernova explosions. And what happens there is the core of the star becomes so, gravity takes over so much that it can compress everything down, so that atoms in the core of this star have compressed so much down so that the electrons have actually, not only were they pushed so tightly together, but there was enough mass that gravity was strong enough that you could keep pushing, and eventually those electrons got pushed into the nucleus of the atom. Okay, so you normally, with an atom, you normally have your protons and neutrons in the centre, surrounded by electrons. Well, what's happened in a pulsar is that the electrons have actually been pushed by gravity into the nucleus. And what that means is that all you've got making up the pulsar are actually neutrons. And that's why they're also called neutron stars as well. And so this is basically showing you how, as you get more and more massive objects, of course a more massive object doesn't necessarily mean a bigger object. You can have a very massive object that's quite small. And how gravity can then overcome the pressure forces. But at each point it does stop. So gravity was pushing here until you got sort of the tension of the Earth. Gravity pushes here on the atoms. We've got those nuclear reactions going on, creating the pressure so it can't push anymore. Gravity's pushed here so that the electrons are so tight together they can't move. And in here it's just gone that one step further and pushed the electrons into the nucleus of the atoms, so that you have this complete star made up of neutrons.
So,
yeah.
When that happens in the process of forming a neutron star, say the electrons are actually pushed in the nucleus, what does that mean happens to the electrons and the protons?
Yeah,
if you only end up with neutrons, is there some sort of annihilation that occurs?
Yeah, so that's exactly, so the electrons and the protons combine to form a neutron, and they give off what are called neutrinos. And it's actually the neutrinos that then go flooding out from the centre of the star. And that's the force that actually rips the star apart in the supernova explosion.
Excuse me?
The ultimate neutron ball.
Yeah.
On your diagram
Yeah.
of the neutron star, what is the small disk or ball that is just above or just around that centre line? You've got an arrow beam of particles and radiation,
Yeah.
and the little disk below that.
You see?
Yes,
Oh, I think that's the Earth. What
as
is
a
this?
comparative size.
No, it's not actually a size comparison because pulsars are actually only about 15 kilometres across. They're actually tiny. I think what this picture is showing is that one of the important things about pulsars, and the reason they got their name, was that they give off, at the magnetic poles of the star, they give off these beams of electrons. And it's pretty much like a lighthouse beam. And so what happens is as the pulsar spins, these two beams of electrons sweep across the Earth. And so that's what you can imagine, that as this beam swept, it would actually sweep across Earth. And that's these guys were actually, the Parkes radio telescope was one of the great telescopes used in finding these guys. And so they emit these very strong pulses whenever you get one of those light beams. And in fact, the pulses are so regular that when Jocelyn Bell, who was a PhD student at the time, saw these pulses, she thought they were way too regular for them to be something natural. And for a little while they called them LGM, for little green men. Yeah. They just couldn't believe that nature could be exactly so precise. And that's one of the things that the guys at Swinburne actually look at, are pulsars and looking at, because they're one of the most accurate clocks that we have in our universe. So there's a whole lot of exciting things about pulsars as well. But let me get back into black holes.
Can I just ask about the planetary nebula first? Is the structure of that more like a donut than a sphere, a spherical shell?
Right. It is a sphere, because basically what's happened is the centre of the star shrunk down and the outer layer has popped off. And so that's completely in a sphere. The reason that we see it as a shell is that we're only seeing the bit of the sphere that's actually lit up by light. And so it's almost like we are only seeing kind of a plane through that sphere. And so that's why it does have this shell-like appearance. And in fact, this is a Hubble Space Telescope picture, and some of the pictures of planetary nebula that the Hubble Space Telescope has found are just completely incredible. They're really, really beautiful objects. Okay, right, gravity. So, the idea is, remember, we've got gravity pushing in, we've got something stopping it. Now, what Einstein told us was that all bodies had a gravitational radius. And basically, what this means is that if you take an object, so let's say we've got the Earth, and somehow we're able to play with that Earth, and imagine that we were actually able to push our Earth and squeeze it and sort of help gravity out, basically, and give it a little bit of extra force. And we start pushing the Earth down. Now, the gravitational radius of the Earth is about 1 centimetre. So if we could somehow push the Earth until it got to 1 centimetre in size, so that its physical radius equaled its gravitational radius, then that would be our job done. It would be a pretty massive job, but still, that's all that we have to do. We only have to push it down to 1 centimetre, and then we could basically just stop. Because once you get to that point, you've collapsed this object to this point where everywhere on the surface of the object, gravity has reached infinite, is now infinite. And what happens is that the object will undergo this catastrophic collapse, and it will do the rest of the collapse for you. You don't have to put any more energy in. And so that's what ends up giving us the idea more of a black hole rather than a black star. Okay? So with the Earth, the gravitational radius is about 1 centimetre. With our Sun, the gravitational radius is about 3 kilometres. This is important, as we'll see in this next slide. So this is basically our picture of what a black hole is. And in some ways, they're probably the most simple things that we have in the universe. There are only 3 things that we can tell about, 3 characteristics that a black spinning round, because of course most black holes are actually formed from stars, and stars are spinning all the time, so therefore of course the black hole is also going to have that spin. And they're probably charged as well. And that's it. Those three characteristics will tell you everything about a black hole. And when you sort of sit down and think about it, what is there, is there anything else that we could completely describe by just knowing three characteristics of it? If you could name three characteristics of something, would someone else be able to guess what it is?
But what about the Schwarzschild radius?
Okay, Schwarzschild radius, what that is. That's also, so that's what this Schwarzschild was. Schwarzschild was actually the guy that came along and solved some of Einstein's equations. And what he found was this radius, it's also equal to what I was calling our gravitational radius, or in more popular terms, popular sort of culture, it's what we call our event horizon. Basically, the event horizon is the point of no return. If you stay outside the event horizon, then you're always going to be quite safe. There's still a whole lot of gravity out there, but you'll be able to leave the gravitational field. But once you cross the event horizon, well, what you're actually doing is crossing the gravitational radius. So you're getting to that point where gravity is infinite. And that's why, as soon as you cross the event horizon, you're going to drop straight into the centre of the black hole. There's no way of stopping it. You're going to be part of that catastrophic collapse. That means that everything sinks down to the centre of the black hole. And we call this centre of the black hole a singularity. And it's probably something that we know the least about in our whole entire universe. The reason being is because the whole mass of whatever this object originally was has now shrunk down to this point we call the singularity, because it can't stay at the gravitational radius. It has to collapse catastrophically. And at the singularity, we've got these two problems, because we've got this incredibly small thing, and so that means that if you want to try and understand it, and you want to go down into the branch of physics which is called quantum, so you want to sort of understand quantum theory to be able to explain these really small things. But then you've got this incredible amount of mass there as well. And if you've got a whole lot of mass, you've got gravity, and so therefore you want to be talking about gravity, which is kind of this huge, large-scale force that normally is sort of, works across these vast distances. And so in that singularity, in the centre of a black hole, you want to try and combine really small things in quantum and the really big things in gravity. And we just can't, physicists at the moment just can't do it. We can't put our heads around it. And so it's kind of this region of unknown, where at the moment all our ideas about physics completely breaks down. There's very little that we can know about it.
So if you have two stars of the same, two black holes of the same mass, they'll both have to have the same Schwarzschild radius?
Yep, exactly right. So they'll have the same size event horizon. And the easy way to remember is that a star the mass of the sun is going to have an event horizon of 3 kilometres. And then you can basically scale things up and down from there. So a star or a black hole that's got 10 times the mass of the sun is going to have an event horizon of about 30 kilometres.
That's the radius, you're saying?
Sorry, yeah, the radius of the event horizon. Yeah. Actually, that leads quite nicely into my next little slide. Because one of the things that I always like pointing out is that whenever I often talk to people, especially students, they always have this idea that, these black holes are these objects that zoom around the universe and they can suck things in and they're doing all of this, terrible damage. But in actual fact, if I was floating out in space somewhere and all of a sudden I, had this pull of gravity, I would much rather be on my way to encountering a black hole than I would want to be encountering a star. Because say, for instance, what we've got here is a poor old comet that's being caught by the gravitational field of a star and also of a black hole. Now, if our star is about the same mass of the sun, then its diameter is, the diameter of the sun is about 1.4 million kilometres. So you've got to hope that the comet stays at least 1.4 million kilometres away, otherwise it's going to be crashing straight into the sun. And then, of course, the other thing is that even when the comet is a long way away from the sun's giving off all this light, it's giving off all this energy and heat. And so our poor old comet gets completely vaporised as it goes on its journey around the sun. Whereas if you had a black hole that was exactly the same mass, so if a black hole the mass of our sun is going to have an event horizon that's got a radius of 3 kilometres or a diameter of 6 kilometres. And so, of course, our comet can actually get much closer to the black hole. So it's, in that way, it's actually, because the black hole is so much smaller, it's an easier body to miss. And so you've got a better chance of being able to orbit around the black hole. And secondly, our poor old black hole, well, the whole point about it is that nothing can escape. Light can't escape, and nothing travels faster than light. And so therefore you don't have all that heat and energy coming off like we do for the star, and so the comet doesn't disintegrate as it goes around. But of course the important thing here is that you do want to stay outside the event horizon, because if you cross that boundary of that event horizon or the gravitational radius, then you're in big trouble. And these are some of the cartoons that I actually got from a book on black holes by a Russian astronomer, and it's just called, the book's just called Black Holes and Other something or other, I can't remember now, but yeah, it's a fantastic little read. And basically what it's showing us is the terrible thing that does happen when you fall into a black hole. Because of course you've got that strong gravity, and what this sets up is a very quick difference in how we feel gravity. So basically, let me take a step back. Even now, as I stand here in front of you, my feet are closer to the centre of the Earth than what my head is, and so my feet are actually under more gravity than what my head is. But because that change in gravity, especially because I'm quite short, the change in gravity from my feet to my head is actually quite small, so we don't really notice it at all. But if I was to fall into a black hole, and say I was falling into the black hole feet first, even with my short height, there would still be this tremendous change in gravity compared to what my feet feel, compared to what my head feels. And that's the reason why you get stretched out. And the classical term that we always use is spaghettified, that you basically get stretched completely into these long, thin pieces of spaghetti as you go falling into the black hole. And unfortunately, what that also means is that anything about you gets completely obliterated. And so it doesn't matter what has fallen into the black hole, no reminder is going to hang around what it is, because you do get so stretched out and basically pulled apart at the seams.
How does that...
Yeah?
Okay, you talked about how the spaghettification works on an object such as you or I, which is essentially just a collection of atoms. How does it work at the atomic level or the subatomic level?
Yeah, so it's basically kind of the same. Everything just gets completely stretched apart, though we're not quite sure exactly how, because this is the problem there when you're now dealing with quantum in this huge gravitational field. What's exactly going on? Who knows? It's hard enough to try and explain what an atom, like quarks, which make up atoms, what they're doing.
Right.
Sort of in normal universe, and then you throw them into this tremendous gravity.
Okay. Yep.
It's ridiculous. And then there's another thing as well, because in fact it's not all doom and gloom, or we think that it may not be all doom and gloom, when you actually do find yourself falling into a black hole. Because if you do, what you want to try and do is you actually need to hope that the black hole that you're heading towards is actually the biggest black hole that you can find. And again, it's one of these kind of contradictory things that often comes up in science. And the reason being is that I've got here sort of two of Einstein-type drawings of models of black holes. And basically, the guy up here is a very massive black hole. And of course, the more massive a black hole, then the bigger the event horizon. Okay? So what this means is that drop down into the singularity because you've actually got a bigger event horizon, you do have more mass there, but your slope is actually a lot shallower. So that change in gravity occurs over a much bigger distance. So therefore it's not as harsh. As if we compare this guy down here, which is for a very small black hole. With a small black hole, it's going to have a very small, mass black hole. It's going to have a very small event horizon. So of course what this means is that our change in gravity is going to occur really quickly, because you go from the point of being on the event horizon to being at the singularity very fast. So the idea is that if you fall into a small black hole, your change in gravity is going to be so rapid that you will get completely stretched apart. But if you go into a big black hole, there may just be that the change in gravity isn't quite enough to completely obliterate you. You may actually be able to survive. I'm sure that's all good news for everybody.
Could be good traction therapy, but then you've still got to face the singularity, don't you?
Well, yeah, there's that. And of course, I think what's even worse is that once you cross that event horizon, there's no way for you to get any information back out into the normal universe. And so you could be having this amazing time on the other side of the event horizon, going into this black hole, but you're actually not obliterated and seeing who knows what. But you can't actually share that experience with anybody else. You can't say, hi guys, you can actually come in here, it's okay.
I'm just saying, unless they happen to be falling in with you.
Well, yes, yeah, you'd have to drag them along.
Forgive this stupid question, but you said earlier that if your head was closer to going to the singularity compared to your feet, that the head area of your body would be stretched further. What if you positioned yourself so that all of your body was perpendicular to the thrusting forces, you would escape it, wouldn't you?
Yeah, not quite. Because one of the things that I did leave out is that, again, it's easiest for us to think about things in two dimensions. So I was basically, just explained it to you as if sort of the black hole was this hole at the bottom and gravity was only in a straight line from my feet to my head. But in actual fact, we are dealing in three dimensions. So there's also gravity tugging on my body. And in actual fact, the right-hand side of my body would be trying to go this way. The left-hand side would be trying to go this way. So you also get pulled in that direction as well. So that's where the complication arises.
So in other words, it's a no-win situation.
Unfortunately. Okay. But just before we go, there's still a couple more strange things that I want to let you know about with these objects called black holes. And I think this is probably the strangest. This is a really hard one to try and tackle. And of course it goes back to Einstein and to Einstein's idea that he's thrown at us that time doesn't always run the way we think that it does. Our common sense is always telling us that, no, the seconds tick by. They may feel like they're going faster when we're actually having fun, but we kind of have this feeling that it's always, the clock's always ticking at this steady rate. But of course what Einstein tells us is that's actually not the case. And one of the things that can make time slow down is if you're in a very strong gravitational field. And so what actually can happen is also, if you're that person that's falling into the black hole and you've got your friend over here who's been very polite watching you as you do it, what they're going to see is actually they're going to watch you just get, your time frame is going to get slower and slower and slower. And in actual fact, they will see you hovering on the edge of the black hole. To them, time will actually, as you approach the event horizon, time will just continue to get infinitely and infinitely slower so that they never actually see you disappear. When in actual fact, you've gone on this journey through. Who knows what may have happened. And one of the very sad things that I've read, I haven't actually managed to find the book, but apparently there's a science fiction book out there that talks about this couple, this guy and this girl that were on a spacecraft, and they were trying to leave the gravitational pull of the black hole. And the guy thought, well, if I can get rid of some mass, then that would make me, be able to leave. What he actually does is he throws his girlfriend out. It's mass. Yeah, it's lovely, isn't it? But of course, what he didn't count on was the fact that her time frame's going to slow down. And she quickly, evaporates and falls into the black hole, what he actually sees is he gets to watch her face as it dawns on her what he's done. And then that face just continues to stare at him because she's still hovering there. So I imagine it's quite a bizarre story. So we do have these things that goes on. And in fact, for a long time, before they actually coined the term of black hole, the things, remember I said that originally in the 1780s they actually thought of them more as like kind of these black stars. Then the objects started to become called collapsars because of this fact that what was happening was you had this catastrophic collapse. Well, for a little while too, they were also called frozen stars because of this idea that when something became a black hole, if you could actually watch it happening, you wouldn't actually see any of the material shrink down because time would appear to slow down so much when you're looking at the black hole. But of course, luckily we do have this concept of black hole, which I think is a pretty good name for it. Okay.
So does that mean that this is probably the hardest concept I think for me to try and visualise what happens time-wise. So something falls towards the black hole as it's going towards the event horizon. You're standing outside watching. Does that mean that it's going to stay there forever?
That's pretty much so.
So does that mean that if you were to look toward a black hole, now the point about this too is that light's not being emitted by the black hole, is it?
Mm-hmm.
Right. So, but does that mean that if you were to look towards the black hole, you would see a complete history of all light all mass?
Yeah, the idea is you would actually still see all the material still on its way shrinking down into the black hole.
So it wouldn't appear black then, would it?
Yeah, the problem is though, is that not only do you have the time slowing down due to gravity, but you also have redshift due to gravity as well. Now, you may well have heard of redshift being used in terms of velocity, and that's what we call Doppler shift. In that objects that are moving away from us, their light appears to be shifted to the red end of the spectrum. And so they're shifted towards the red end. And so, for instance, a quasar that's giving out optical light, because they're moving away from us so quickly, that light is no longer optical light, it's moved into the red end, and so we don't see it anymore. Well, that exact same thing happens when you're in a gravitational field. It's not because the stuff is moving, it's because the material is trying to overcome this gravity. And so what it has to do is it has to give up energy. And so therefore, instead of it being optical light, for instance, again, it's moved into a redder part of the spectrum, which means that then we don't detect it, we don't see it. And so that's why we do see it as being black. You can't pick it up anymore because of the gravitational redshift. Interesting question.
So that means that image of my wife, for instance, would you're talking about girlfriends, don't tell her. She's not here. So what, that'll just fade?
Exactly, it does fade, yeah. And because what's happening is that image of her
is getting redshifted.
Has been redshifted.
Yeah.
And actually a great thing that a friend showed me recently was, if anyone's the series Stargate, they actually did an episode on this kind of thing, and it was fantastic. I've got to try and get a copy so I can use it. It would have been great to have shown it to you tonight. Basically, they fudged it a little bit because what they said, there was this black hole on the other side of the Stargate, basically, and what was happening was that everything in the Stargate all of a sudden got into its own little time zone compared to the rest of the world. And so you had people leaving the Stargate Centre and, going and spending weeks outside and coming back, and in fact only, a few minutes had actually happened because they were in the vicinity of this black hole. The thing that I'm saying is they fudged it is because they actually had that time effect happening before they felt the gravity of the black hole, which isn't correct. And they did say that in the thing. That was one of the things, that puzzled them completely, because they should be feeling the gravity at the same time that they were feeling the time effects. But, of course, it made for another better episode to be able to to see that happening. And one of the other things too is that they took a photo, and the photo came out all red. So the light had been redshifted. Which again is a bit iffy, but it got the point across. Yeah, exactly. Okay.
Tanya, I don't want to labour the point on this, but one sort of stuck. It's my wife and not my girlfriend.
Right.
And I'm watching her on the edge of this black hole. She appears to be stationary.
With this look of horror in her face, and how could you
She'd
do
have
this?
more than that, I think. What she's experiencing.
Yeah, for her, she has actually passed through. The thing is that for her, the time hasn't slowed down. And so she is actually, it's a bit hard to explain. She's thinking that the seconds are going by like we've got seconds now going by, so completely normally. And so, you know, in what feels like 10 seconds, 30 seconds, she's crossed the event horizon and has been completely obliterated. Maybe she was lucky and you chose a big black hole for her and she might have survived. But what's happened is that when you look at those 30 seconds, even though she thinks they're going like this, to you they're going like that, much slower. And so that's where the difference occurs. She doesn't have any extra time to panic or worry. You can just see her for so much longer. It's your perception of her time.
So with Einstein, we say it's a relative.
Exactly. It's where it all comes back to.
If the boyfriend walked backwards while he was watching her, wouldn't he see her fallings to some extent? Or less expression on her face?
I mean, certainly, I suppose the more distance you're going to cover, the blurrier things that she will see, certainly.
You're trying to introduce some redshift, though.
Yeah. Okay, I know it is getting a bit late, but there's just a couple of other neat things that I do want to say before we finish off. Another kind of crazy thing about these black holes is that, as I mentioned, they're spinning, because all stars out there are spinning. The sun is spinning. Of course, so is the Earth as well. But and what happens when the black hole spins is that basically it doesn't stay circular. It becomes flattened at the poles, and this is something that we see in, just in our solar system. The gas giants, for instance, Jupiter and Saturn, Uranus and Neptune, they're all, because they're made up of gas, so they're a bit more kind of malleable. And as they spin, they're actually not complete spheres, they're kind of shrunken at the poles of the rotation. And that's what happens with the black hole. Basically what it's doing is it's almost like it's dragging space, because remember it's making these big, the mass of the black hole is made these big indentations in space, and as it spins it kind of drags the space around it. And so what this sets up is your event horizon is actually always circular, but you've got this, because of the rotation, you've got this kind of oval or elliptical type shape. And this region in between here, so you've got the event horizon circular, and then this elliptical region is what we call the ergosphere. And the idea is that you can cross into the ergosphere, and you still, as long as you don't, at the poles you're in a bit of trouble, because the ergosphere and the event horizon actually meets, and so once you're crossed, you're into the black hole and you're obliterated. But if you're lucky enough to enter in this part of the black hole, you've actually got this little bit of space here where you haven't yet crossed the event horizon, and so that means you've still got a means to escape. You can still actually leave the black hole. And this becomes very interesting when you think about energy production. And again, this is from this same book. And it's got the idea that maybe one of these days we're actually going to be able to get out and explore the universe, and our fuel is actually going to come from these black holes. And the reason being is what basically the concept is that if you're in your little spaceship and you cross that ergosphere, and what happens is you're caught up in the energy of rotation of the black hole. Now you could just sort of coast in, you don't have your rockets firing, you've crossed the ergosphere, but you haven't hit the event horizon, so you're going to be able to escape. And what you do is you need to position your rocket so that the rockets are actually pointing towards the black hole. Now the idea is, you turn the rockets on, the fuel's going to fall into the black hole, you're going to escape the black hole because you haven't crossed the event horizon. But apparently, when you escape, you actually pick up more speed than what you would if you just had turned the rockets on and you were, just in normal space. You've actually, for the same amount of fuel, you get a much greater velocity. You get this much greater, a much bigger speed, and lots more energy given off. And the idea behind it is that what's thought to happen is that you actually take energy from the black hole. You take energy from the rotation of the black hole, and that then gives you that extra push to make you go that bit faster than what you would have normally done by rockets alone. And I think it's, it's kind of analogous to, I'm sure you've probably heard about the gravity assists that we give our satellites. Like, for example, Cassini, that's on its way out to Saturn. It orbited around Venus, I think it was Venus, a couple of times, to pick up some of the rotation of the planet Venus and help it sort of push its way out into the outer reaches of the solar system. And the idea is that that's what you can do with a black hole as well. If you enter this ergosphere, you can actually you can slow down the rotation of the black hole and take some of that energy with you and of course it's probably a lot more energy that you'd end up taking than what the satellites do using the planets. And so that's, who knows when we may end up being sometime in the future. And just to finish off, we might as well finish on the fact that these black holes, they're not thought to actually always be around. The idea is that there is a way of getting rid of a black hole. And this is actually called Hawking radiation, after the famous astronomer Stephen Hawking. And again, it's kind of one of these crazy ideas. It's the last time I'll stretch your brain too much for the evening, unless it's people like going into a black hole itself. What this is all about is that apparently what we always have in a vacuum, so you've got the vacuum of space. In fact, what we know is that it's actually not a vacuum. There are what we call virtual particles. And these particles can appear, and within a fraction of a second, they collide together, and they annihilate each other, and they disappear again. This is something that is measurable in vacuums here on Earth. That, they've been able to find these particle pairs that will just spontaneously appear and then annihilate again and disappear. What Hawking says is, space is pretty much a vacuum. And so he says, well, what happens if, imagine this is the event horizon of your black hole, and what happens if the poor virtual particle pair that spontaneously appears, what happens if one of them is lucky enough to appear above the event horizon and one happens to appear below the event horizon? And of course it's quite probable that this would go on, because there's nothing physical that actually marks that event horizon. Okay? And so the idea is well, if you've got one that's above the event horizon and one that's below, the poor guy that's below, down here, he doesn't have a choice. He's got to fall into the black hole. He's crossed that point of no return, that's where he's going. What I suppose he does is, in a way, he kind of sacrifices himself. Because what he does is that he gets added to the black hole, and what it means is that this particle can actually escape. And when the two virtual particles, when they actually get separated and they don't collide again and annihilate each other, what happens is we say they become real particles then. And to make them real, you've got to give them energy. Okay? And where this energy is going to come from in this case is your energy is actually going to come from the black hole itself. And so in actual fact, the black hole is going to be losing energy because it gives its energy to these two particles, gets some of the energy back because of course this particle does fall into the black hole, but it also loses a little bit of energy as well. And that's the problem. And so what Hawking radiation means is that in actual fact, a black hole isn't truly black. It is giving off this little bit of radiation in these tiny little bits of energy, these tiny little particles that are actually becoming real and being able to escape. Yeah?
Excuse me, I read somewhere where a black hole evaporates.
Yeah, so this is this process. So basically it starts off very slowly in that it's only evaporating at a very, very low rate, so that the energy or the temperature that it's giving off is actually almost absolute zero. You would hardly measure it. But the idea is that this process can kind of end up basically, can sort of gather momentum and basically keep going. And as the black hole gets smaller and smaller, then you can have more and more of this Hawking radiation given off. And it's thought that when it becomes a certain size, in fact, all of the radiation will be given off in one complete blast. And so you may well sort of see these flashes of light as the black hole completely evaporates and disintegrates. Now, the problem is that if you had a very small black hole, so a black hole that's only sort of a few thousand tons, and that black hole formed at the beginning of the universe, then it would only be now, 15 billion years later, that it would have had enough time to evaporate in this way. And so we may well see these flashes of light. They would only start to appear now. So that's a bit of a problem in trying to test Hawking's theory, because with black holes that we know about, these stellar black holes that are about 100 times the mass of the Sun, it's going to take a lot longer than what our current age of the universe is for it to finally get to the point where it completely evaporates. And so there are, there is a little bit of a problem there in that, will we ever get to see this happen? And one of the things I think that Stephen Hawking also proposes, that maybe there were what are called primordial black holes, quite small black holes that did form at the start of the universe. And if so, then we may well be about at the point where we could start to see them evaporating. But there's a lot of kind of ifs and maybes in there, I think, that we shouldn't get too excited right at the moment. So sorry for taking you a little bit over time, but I did enjoy all the questions and everything that you asked me of me, and yeah, it was, once again, I quite enjoyed it. But you did too. Come on.
Once again for coming down to visit us. Ian, have we got a small gift? And we'd ask you, of course, to stay around for the rest of the meeting, and I'm sure you'll get coddled by people asking you other questions.
Yeah, I think that might be the best way to do it.
It's not gift wrapped.
Thank you very much.
Thank you very much for your job. Well done.
Oh, thank you.
Well, given the time, I think we'll break for a tea break now and reconvene in here in half an hour's time, which should be, let's say, 10:15. And we'll show some slides on the Mercury transit at that time, sky for the month, and also something on the planet walk in Switzerland.
Is there a video?
There'll be a video currently going on next door on the day of the sun.
So, okay, you run out of fuel, fusion emissions, Well, it's just not going to be culmination, basically, to give it
It's an enticement. I should draw the reference.
Exactly.
Girls are awesome, but
So it's supposed to celebration. Yes, we can check that out.
regularly.
Yeah, that it runs beautifully.
Basically.
Pretty much, because of course we're going into show production. So basically I'll be doing the final touches on the show and then going out. I know.
More shows coming in.
We do. We've actually got a season of pictures. They're coming on board and we're putting together a show on MPAS. Last one was a sneak preview that's going to be almost in a time machine. Last two books. Last Yes.
Well, it would
A challenge. It's like to push the
be share now.
The quiz program.
Yeah, it's just nice. That's just called security. I guess it off now and again.
But you just got it on there just to...
Yeah, I have
just completely lost touch.
just security.
Yeah.
Yes, indeed. Yes.
See?
Oh yeah, that's it.
So I just,
No, you
I just want to take up this on. I have it on the drive.
Just remind you as well.
Yeah, well,
I'll just go to lots of money for one telescope.
it seems to be passion quite good actually.
Does she give them a receipt?
Just,
So she should give the receipt.
It's
Well, before she's
Yep.
going
She's got the receipt. Okay, so I'll tell her at the
Like the very last one, the one where you do space line up to the side. Okay. The one where you do space line up to the No, we'll do space line up. Impossible. Oh, that's quite. Oh, wait.
My music problem is listening to too much. So it's keeping me inside.
You get details.
I'm stereo.
Not in the field.
No, one uses these things as one uses these. Yeah. It's hard to play around on the outside.
Draw the raffle.
You can draw the raffle.
Oh, I think that's
Number 6.
Number 6.
Number 6. Okay. Take your pick of the 3. Next one. We're drawing the raffle.
16.
16.
Number 16.
16.
Number 14.
14.
Oh, yeah. I think so. Yes.
Okay, let's move along before the night gets too late. What we'll do now is we'll have a few slides on the Mercury transit, which Ian Sullivan will show, and then we'll have Bob Heale Sky for the month, and then depending on the timing at the end of that, I may or may not talk on the planet board. Yes, whichever one you like.
Yeah.
Okay, we don't have ticket number 16 at all. No, all right, we'll wait and see if they come in. Now, one thing I wanted to point out, next month, there's a minor planet occultation that's naked eye. In other words, you'll be able to see an asteroid pass in front of the, potentially pass in front of the star Beta Virginis. As you can see here, the shadow of the asteroid will pass over Australia. There's quite a bit of uncertainty in where it will actually come. It's a lump of rock basically about 80 kilometres wide, and on June the 24th at about 8:30 in the evening it will pass over, and if you're looking at the star Beta Virginis, which is a magnitude 3.6 star, you may see that star disappear before your eyes. And what we'll be looking at is trying to get as many people across Victoria to actually be looking up at that time, either with binoculars or with unaided eyes. If you've got a video recorder, an ordinary video camera, you'll be able to record it successfully at magnitude 3.6. So the minor planet is magnitude 13, which means you'll need at least a 6-inch telescope to see the minor planet, but with your eyes you won't be able to see the asteroid come over, but you may be able to note the disappearance of the star. And from that we can actually deduce what the shape of the asteroid is if we have enough people across Victoria looking at it at that time. But more will come out on that next meeting. Alright, we'll go over to Ian. Yes, I'll have copies of that next meeting. Yep. Lights down.
First of all, as a commercial, people asked about getting duplicates of the eclipse slide done, and I've got both done. The African eclipse, so
Number 1, yeah.
you go forward. That's the African eclipse. That's the original. You can focus just a tiny bit there. That's it. That's not bad. Pretty good. Yeah. Okay. That's the original. Right. Next. Yes. Something's gone wrong. There should be 2. That is Seduna. But you should be 2. Well, you missed a slide somewhere. Go back one up.
Just press it.
No, go back one.
Go back.
Go back one. Go back one. Anyway,
It's called down the black hole.
anyway, go forward, Alex. That's the. Good God, what's going on?
Well, that's it. I'm just pressing the button.
That's the Seduna eclipse. Next one. That's the duplicate of the Seduna eclipse. Now, the thing about it is, it's $3 for one, $5 for the both in an envelope, and they're both labelled. right? So if anybody wants to see me later tonight, or I'll bring them again next meeting. If anybody wants to buy duplicate slides, you want them for your collection, all right? Okay.
Will you take them next?
Yes. Okay, next. That is the one that should have been back. That's the duplicate of the applicant. Now it's got out of order. Okay, next. Okay, now I drove in a vehicle, unlike persons around here who stayed home, drove up with Jim Blanksby up in northern Victoria looking for clear sky, and we had to drive a long way. We finally found it towards Sea Lake, in the Sea Lake, and there's Lake Torrens just here. This is the stream leading from it, and there was clear sky when we got there. We had it for about an hour and a half. So this is for the transit of Mercury on the 7th of May, which I think most of you did see. Right, so we're setting up. Here we go. We got a nice big double sun. Right, so next. Could we have all the lights out? We don't really look. We're going to. Big close the door. Close the whole door. We wanted we went in every bit of light we can get. Right, you can see this Mercury. It's not gigantic. This is just the creek and the science. Right, next. Right, now you can see there, nothing. No, wait a minute, I can. See a tiny bit here?
Hi.
Tiny over there?
Right.
If I can. I think I could. Okay. And the sunspot. Just focus slightly on it.
Okay. Just a sec.
Yeah, that's about as good as we'll get. Other way.
Yeah, it's there.
Does that move? No?
No,
Righto, okay. Righto. Next. This is about 3:15 in the afternoon, and there we are, just there. See it on the... Just on the edge, right. And the sunspot, quite a sizable sunspot, so that's something as a marker. Something to focus on while you're trying to get yourself together. Right, so... Right, next. And there it is, clear. So between first and second contact, and then of course after second contact. Next. There it is. I changed exposure from 500 to 1,000. Sort of went from one to the other, just to see. We wasn't sure what the contrast. If you're overexposed, I'll show you one a little later. You'll see what happens. Next. There we are. That's 500. You can see that's a 500 to 1,000. There we are. There it is there. Next. And that one, see, there's a little cloud over there. Tiny bit of cloud. Don't see, there it is. Still visible. Right, next.
Next, yeah.
Keep going. Cloud, more cloud. Yep. There it is. Next. Yep. Next.
Upside down.
Here it is. Flipped over. Right. Right. Next. And here it is. Next. Now this one's flipped over too, sorry. You see this is at 2/50th of a second with a higher exposure. See it's just about washed out. Just see it. So your exposure is quite important. It's better to underexpose than overexpose. Right, next. And the clouds descended about 5 o'clock, and that was about it. Yeah, okay. I can't see it. I don't think it's visible there, no. Okay, next. And that was my telescope. That's the Questar here. This is Jim Blanksby. He's got a Vixen 6-inch here. He's taking pictures and all. That's right. Okay, next.
Did you get some photos, right? Did you get photos?
Yes, he told me over the phone he did, but I haven't seen it. It's not as clear as it could be, is it? Yeah. Next. Yeah. Yeah, that's right. Next. And there we are. interesting. We had jet planes racing around the place, and so we were getting these cloud formations. Things were changing, right? But, you know, what was natural, what wasn't next. Yeah. And the sunset came up. That was the end of it. Interesting afternoon. I've got a few slides here about transit. Have we got enough time, Mr. President?
Yeah, more minutes, maybe.
What's the one more? Okay, next. This was a book that's in our library here, and I've got the picture from it. There's your transit there, you see the dot, see the, that's the symbol for Mercury. This indicates the alignment, the inclination of Mercury orbit in relation to the Earth's orbit, which is the ecliptic, and the lining up. And these are transits have occurred, or going to occur. Notice that the whole series of them, that's 2000, here we are, 1980, 93, 1960, 2006, 1973, 1986. Notice they're all parallel, but you see the ones that are the opposite here, 2003, 70, 2016, and they're all different angle. Anybody suggest why?
On the other side of the earth.
So,
Different month.
what about the time? Yes.
November.
We have November and May. Those three that are at a different angle are in fact May transits, not November. Okay, next. You see all of these, they're all November transits. That last one 99. See all parallel different times. Okay, next. And this 2003 is that area there, which I've shown you before, that area there, they're the people in that area, this area here, saw the entire transit. If you weren't in that, you would not have seen the whole thing. Of course, we missed out, we only saw the beginning, that's why we're here. Next. I showed you this before too, and that was the situation November, May, it's going slower. So that situation would be 4 degrees, wouldn't be as much as that. And then this figure is different, would be less. And of course when you divide, you work at the degrees moved over the difference in degrees per day. This is this figure here. The degrees moved is worked out from the position, the ratios. Can you focus that a bit better, Alan? Anyway, it works out to about 6 hours by just working that one. That position 0.4.6. Right, next. And this shows the November-May situation. This is November and this is May. You have less transits in May, but when you do have one, it tend to be longer. Not for certain, but they tend to be longer. This is your feeling. Mercury is whizzing around here about 4 times a year, while the Earth goes slowly around. The Earth, of course, will be in those months.
Well, Mercury should look bigger in May too.
Should look bigger because it's nearer to us. Yeah, it's nearer to us. Okay. Size, because it's about 12 seconds of arc rather than about 10. Okay, next. These were, when you're looking for cycles, just like eclipses. Now we get a repeat of an eclipse after 18 years, 11 1/3 days. That's called the Saros. You get repeats in Mercury transits. You just do it by multiplying these times, multiplying Earth times, revolution times with Mercury. And if you get two that are very similar in length, not identical but very similar, you'll get transits will tend to repeat each other. And so you get these times when you can run one into another. The year is a 46-year cycle, and a 263. Yeah. Yep. Those are the times. And then here are the, and down below, yes, the the May transits and the big type. And there's 1924, 1970, yeah, 2016. That's right, 46 years. 46 years, there we are, so this year. Okay, next. And you see there's 46 years in between all of those, 217 years this way. These are May transits. Right, next. The size of the Sun as seen from the various planets. From Mercury, that's the size of the Sun. From Earth, this is the size. You see, it's quite a bit bigger when you're on Mercury. As you go out from the Sun, of course, that means that the path of Mercury's got less distance to travel because the size of the Sun's smaller. However, the planet is going, you're actually going slower. You're going up further, so the transits don't take less time, they tend to take longer. Right, next. The coming transit, 2006, that one, early in the morning, on Thursday, November the 9th, 2006, we can look forward to that. And we'll see the whole event, except for maybe just the beginning. I might miss the start of it. And Venus next year, the transit will be virtually a repeat of what we just had on May the 7th. We'll only see the first couple of hours, and again, very similar to what we had on May the 7th, the planet Venus. And then Venus will repeat again, and we'll see the full event, weather permitting, of course, in Wednesday, June the 6th, 2012. Next. And lastly, this is the transit of Earth going across the face of the Sun as viewed from Mars. So a Martian would see this in 1905 and 1984. Right? So Martians will experience the Earth transit the Sun. I think that's the last one. That's it.
That's it. Okay, Bob, you can set up the sky for the month. And do we have number 16 raffle ticket turned up yet? No. Just like that.
How do I get this going, Rita?
You got 6 minutes?
Yeah.
Okay, get cracking on this. I think I'll leave the lights on. I think they've installed new lights, so the colours are good. Yay! Okay, as Ian pointed out, views of Mercury are still good. So for our morning sky, Mercury is going through a fairly high path, even though it's 10 degrees in altitude. It's in a dark sky, and for the viewing month, it reaches its peak early June. And you can pick whichever morning you like to see Mercury fairly close with descending Venus, and also Mercury descending after early next month. So good views for Venus and Mercury for a little while yet. Saturn is almost history. Not quite a total dark sky, but as we move into winter, it does get darker, and we'll still see Jupiter following Saturn, albeit slowly, but Saturn's almost history in terms of its view in the evening sky, and Jupiter will follow. Okay, Mars is brightening. Look at that, almost double the brightness there. It's touching for mid-June about magnitude -1, and it reaches magnitude -3 by August, I think. The accurate ones can tell me I'm wrong, but I think that's about right. So it's
Having these lights on quite a lot, it makes it hard to see.
oh yeah, I can knock them off a bit. It's just all right, fair enough. All right.
Second from the top.
Second from the top. Okay, that's the presentation.
Going back to where we were.
Yeah, no. Do you want full darkness?
Well, almost that. I mean, what's the point of having lights if we
That's as best as it's going to go. Which one of these, Peter? Well, I can't see the computer screen.
That's when she got your little lights.
Yeah, okay. Rightio. Okay, left with Mars there. Okay, the night sky. With respect to the Messier month, or the Messier viewing night coming up next Saturday on the 31st, I'll just mention something in particular with respect to that. Absolute heaps of Messier objects on the chart. They're all within moderate binoculars or a small telescope. There are two objects I'll sort of briefly mention. There's a moderately reasonable double in Corvus, New Corvus, up there, and I'll show you, and you're probably never going to see it unless you're slightly higher in latitude, the Black Eye Galaxy simulated, but you'll see something resembling it. That's in the constellation Como Berenices, which is around that area, but I suspect it's too low. A miracle might happen and you might see it rising in the eastish. Okay, so you've got that on your sky for the month, so there's really no need to say much more about that. Okay, similarly in the southern sky, absolute heaps of Messier objects in the Sagittarius region and Scorpius, a few smatterings around. I'll concentrate on two objects very briefly. M83, which is more of a filler, and the fairly reasonable double Beta Scorpii. And then I'll mention the Messier thing for next month, on Saturday the 31st. Okay. Okay. Black Eye Galaxy, M64 in Como Berenice, and there's a bonus cluster, MEL 111, or commonly called the Coma cluster, and I've just mentioned that you've seen this before, but it's better now, as you can see that little bit there. Okay. Right, this is the region of the Como Berenices cluster, which is left of Bootes. The shape of the constellation is formed by those three bright stars, and there's the mellowed 111 cluster that's visible with the eye, and it's a typical Y-shaped asterism. And you'd have to go to higher latitudes to possibly see it. Similarly with the Black Eye Galaxy, it's basically in here, but I'll show it to you nevertheless. Simulated, kind of everything. Okay, that's a slightly blown up version of it. There's your asterism, a little bit more magnified, and M64 is in the trapezoidal shape there. It's called the Black Eye Galaxy. I wonder why. Whoops, I did that. Okay, I pinched, the simulation comes from Michael Stecker's photographs. I've cheated a little bit, so it's sort of a colour thing. It's a fairly wide oval-shaped galaxy, and it is visible in binoculars. There is a claim that in large binoculars, the dark lane, which I've got there, it actually should be shifted a little bit. The inner bit looks just like that, in a colour photograph of course, and the dark lane is sort of tilted, it's shifted more to the upper edge where the red line's going across. But the Black Eye Galaxy is basically because it's got a dark lane in the inner brighter region, just like that. And if you hit it with a good telescope, you see that. Okay, that's the Black Eye Galaxy. It's not far from actually what it looks like. That should be a little bit more curved and displaced to the left. That requires a little bit of finesse with computer programming. Okay. The Delta Corby one, you've seen this before. Okay. There's the region of Corvus. There's traditional outline of it, and we'll home in on that now. Okay, there's Delta Corby, and it's got a very magnitude 9 companion. Delta, the primary there, is supposed to be, some people claim it's a bright blue. Some photographs are showing it's got a greenish tinge, which is accidentally occurring there now. Okay, and if you hit it with a telescope, it separates completely and you see the light blue companion. So that's Delta Corby. It does, you get that with a 4-inch telescope at about 40 times. Okay? Delta Corby. Remember, it's the little blue one there. Okay? That's just a field star near it. Rightio. Southern Sky, Beta Scorpii. Beta Scorpii is an optical double. It's an optical double with its nearly equal, roughly equally bright companion Beta 2, but Beta itself has a true companion at magnitude 10. Okay, let's see if we can find that. Alright, reference is basically Antares, and this is an image at culmination, moving up to the T part of it. That's the star there, the white one. So a little bit higher magnification, nothing yet. Okay, a bit more. Starting to separate now. Now they are, I believe, optical companions. Beta 1, Beta 2 is the top one, and when we use the equivalent of a 4-inch telescope, you see the magnitude 10 companion coming out from Beta 1. That's flipped over, okay? That's the main one. That's Beta 1, that's Beta 2. And that star is a companion to the brighter pair, okay? Don't sort of get confused. The optical companion is that one there. That's the white one's the true one with respect to the top. Okay. That's it on the computer thing. And to finish off, I'll just turn that screen off. Once more. Okay. Just say a word on the Messier Marathon. On Sky for the Month, you've got a few finder charts, particularly for the south sky. These little black things below. With a bit of luck, we might have some people doing that on Saturday the 31st. Those finder charts are for straight-through finders or binoculars, okay? So you need to turn them that way if you are looking through a telescope. It's not for every Messier object, but each of them has at least 2 Messier ones. And there's similarly one for the northern sky. The other thing that I did, which may or may not be of use to people, John did some sheets on the RA index of Messier ones. This is this came from Astronomy Now, 1998. It's the entire Messier catalogue. I've got, I think, 4 of these, and we probably won't have hundreds of the Messier hunt. And it's got the whole lot. right through, back to back, and there's a comment near the end explaining why 3 messier objects have been deleted. M40 that doesn't exist. That's a double star in Ursa Major. M73 is an asterism in Aquarius, which you'll only get in the morning sky of the 31st anyway. And M102 is a duplicate of M101, which you probably won't get because it's in the northern sky. Okay, so for those who are really, really keen, and for any official that wants to know what people really have in their telescope and want to verify, there are the images. I'll just keep one for myself. I'll provide the backup with my computer telescope just in case people can't find things. Okay, I'm done.
Thanks, Bob. Have the slide projector on, please. You can see it? That's right. Okay.
I might have to turn the switch back from internal to external. Let's go to trouble. No, it's around the other side.
Yeah. Well, while they're turning that on, I would remind you, if you're interested in Astronomy 2003, that I think we've got only 2 left or 3 left for the whole year, and that's what shows what's in the night sky throughout the year. And also solar eclipse posters. We've got one example here of the one that we can get members for $12. Normally they retail for $20, but you can bulk buy. And the Society will have those in next month. So if you want to pre-order one, please note down your name. Please give me your name tonight, otherwise we won't order in excess. We will only order in those that we have on order. And if we're waiting for this one, what I'll show is a couple of slides that I took from Frankston of the transit of Mercury on the 7th of May. And it showed that you didn't really need to go all the way up to the top of Victoria to actually see it successfully through the cloud. Get there. Basically, it began just before 3:15 in the afternoon, and quite a warm afternoon down here it was as well. And the cloud came in, started to come in around mid-eclipse down in Frankston, and not mid-eclipse, mid-transit, and by the end of the transit you couldn't actually see the sun at all. It really came in very, very thickly. So not too different to what Ian experienced further north. Okay, can you flick the first one on?
Is that all in the no,
You missed it?
what's going on here? What number do you want first, Peter?
It's about 40 or thereabouts. 40.
Oh, that's the problem. Yeah, okay. It's nowhere near, right? You'll be going on forever. No, back one. Right, that's the first slide, right?
That it? Yep, it'll do. Basically, that's where I set up looking over Frankston Pier, which is there. And this is up on the hill where all the churches are. If anyone here is familiar with Frankston, there's their new little bridge over there. That's looking there, and the sun is eclipsed behind the telegraph pole. Okay, have the next slide, please. So here we have, looking through my 6-inch telescope, which is actually identical to Jim Blacksby's one, through a Type 2A solar filter. It's a little bit out of focus. You don't actually see Mercury on that shot. This is just prior to the transit beginning. We go to the next one. And I'm not sure if we can see Mercury. Yeah, it's a little bit out of focus. Now you'll notice Mercury actually comes in on that side with mine.
That seems to be a ski side.
Yeah, okay. Move on to the next one. Yeah, you can make out Mercury just coming in there. Notice that? You can get that into focus. Time. So it's just come through first and second contacts there. Okay, move on to the next one. There it is there, slowly moving across. This is all at prime focus on the telescope, which is the equivalent of using a 750mm lens on the camera. Okay, move on to the next one. And these are typically in 10-minute intervals, so you can see it there slowly moving across. Next one. Go through it fairly quickly. It's a bit clearer there. Next one. There There it is there. Next one. It's there. And there. So as you see, it's all quite clear, no clouds in the way. Next one. Now this was a bit of eyepiece projection, and I'm always lousy at getting the good focus on an eyepiece projection. But there's the planet Mercury there. Okay, move on to the next one. So that was around, in fact I think that one was actually at mid-transit. There's the next one there, may have moved a little bit, it's a little bit blurred there. Okay, next one. Then the clouds came in, and as you can see the wispy clouds starting to come across the face of the sun there. And the next one. And still a bit wispy there. And the next one. And that was pretty much it.
You're talking about mid-transit there?
Mid-transit, sorry, I was saying.
Yes. That's not possible, because it was 5 hours, 18 minutes, and the sunset came before mid-transit.
Quite true, yes. Yes. Mid-time between start and sunset. Okay, does anyone else have anything else to bring up before we close the meeting and get thrown out by the security guards?
Oh, there was a nova discovered last month in Sagittarius. You know the teapot Sagittarius. It's right on the bottom of the teapot actually, and it was discovered by a Japanese chap and also an Australian. And initially it was around about 9th magnitude, but going back through records they found it had been brighter than that. It faded down a bit and then it flared up a week or two ago, and I made it about 7.7 magnitude on one night anyway. And it's now faded down again, down beyond 9th magnitude, the last I heard. I haven't seen it for a few nights, but it was quite easily visible. So in other words, it peaked up, dropped down and peaked up again. So it had two peaks, now it's going down. Right.
Okay, thanks Bruce. Okay, well thank you everyone. I hope
next meeting, it's on what's on there, it's got life on Europa. It's supposed to have a question mark after that. We accept the fact that there is no life on Europa.
Ian's right. Tony Shulkin is coming down from the ASV to speak to us about life on Europa, not from personal experience, no doubt, but speculatively.
Life on Europa
question mark. Okay, well thank you everybody, and we hope to see you at June's meeting. Thank you. Smart answer.